Welcome back to this channel. This video will be the last part of chapter 3. In this video, we are going to focus on the definition of electronegativity, and then next we are going to discuss about the variation of electronegativity go across the period and also going down the group. Last part of this chapter, we will discuss about the acid-base character of oxide for the element in period 3. Before we discuss the variation in electronegativity, we need to know the definition for electronegativity first. So, electronegativity is the relative tendency. In bahasa, we can call this as the keupayaan, or another term we also can know it as ability for an atom to attract bonding electron. Okay, so here we emphasize the word bonding electron. So where we can find this bonding electron? Yes, the bonding electron always is in a covalent bond. Let's look at the diagram here. As we already see here, there is hydrogen and chlorine. So both hydrogen and chlorine are non-metal, so they are going to form covalent compound. So in this, through the covalent bond. So in this covalent bond, they are sharing electron, and then this electron will be known as bonding electron. Okay, then now let's take the periodic table as the example. Okay, you will notice that there is a number at the bottom of each element here. Okay, but this all number is not referring to the proton number and also not referring to the relative atomic mass. So basically, what is this number represent? Okay, so basically this number are called as Pauling scale, where we use them to determine the strength of the electronegativity. So when you go through this, you will notice that the range is only from 0.7 to 4. Okay, so the lowest 0.7 is at here, bottom left, and the highest 4.0 is at the top right here. Okay, so again, based on the definition and the value, we will get the idea that the greater the value, the more electronegativity the element. Okay, so now we try to look at the trend where across the period. Let's take period 2 as the example. The scale increased from 1, 1.5, 2, 2.5, 3, 3.5, and then followed by 4. So we know that the electronegativity is increased when going down the group. Well, we look at the example of group 1 from hydrogen 2.1, 1.0, 0.9, 0.8, 0.8, 0.7, 0.7. When going down the group, the electronegativity is decreasing. So let's after go through the trend, then now we are going to do the explanation about the variation across the period and also down the group. So here again, we will see that across period, proton number increase, atomic size decrease, which means the effective nuclear charge also increase. When the effective nuclear charge increase, attraction between nucleus and bonding electrons. Okay, so you see, we are going to explain according to the definition. So in your explanation, you have to emphasize bonding electron also increase. With this, electronegativity across period will be increased. When going down the group, the principal quantum number increase, the number of shells occupied by electron also increase. Then cause the shielding effect increase, attraction between nucleus and bonding electron decrease, so electronegativity is decreased. So far we already discussed about radius, ionization energy, and also today we continue with the electronegativity. Always across the period, you will notice that we always use the factor of effective charge. While going down the group, we also always use the factor of shielding effect. So do keep in mind, always use effective nuclear charge to explain variation across the period and shielding effect when going down a group. Okay, now let's proceed to tutorial question number 9. We are given the proton number for element X and W, which is 12 and 17. And then this question asks us to compare the electronegativity between these, and then we need to do the explanation. So means that we have to always, before we start to compare, we need to write out the electron configuration so that we will have the idea, these elements are in the same group, same period. Okay, so based on this electron configuration, it's very obvious, up to 3s2, 3p5, and then also 3s2, means that they are from the same period. At where element W is in the group 17, while element X is in group 2. Okay, so then as we know, across the period, electronegativity increase. So in this case, we can come out the conclusion that W has higher electronegativity. Okay, than X. Then now we need to do the explanation, because across the period, W has smaller radius than X. And when the smallest radius means that they will have the greater ability to attract the bonding pair electron. So you see in their explanation, they emphasize the bonding pair electron toward itself. Okay. Okay, let's do a very quick summary based on the three factors, actually three characters that we already discussed. For example, the first one, atomic radius. Across the period, the size getting smaller. While going down the group, the size getting bigger. So end up, we have the conclusion that as long as if you're comparing the elements from different period and different group, then we will try to check using these tips. At the bottom left, consider the atomic size is bigger. Okay, while the trend for the ionization energy and electronegativity are same across the period, the value of IE is higher and also greater value for the electronegativity. But going down the group, the IE and also electronegativity will decreasing. So end up we have the idea that at the right top here, normally IE and also the electronegativity is greater. Besides that, we also will study about metallic character, but this metallic character will be emphasized in chapter 4. Okay, however, I just share with you. Okay, as we all know, metal is, group 1 element is metal, and then group 14 has 13 and 14, some are metal, metalloid, and non-metal, but basically non-metal will be group 15, 16, and 16, 17, 18. So at the right side here is non-metal. Okay, so for this here, we know that metallic character will be decreasing across the period. While for the metal, for the group 1, when going down, the group 1 metallic character is increased. Okay, but for the non-metal side, if going down the group, the metallic character also getting higher. So that's why end up bottom left also showing greater metallic character. Okay, we are at the last part of the chapter 3, which going to discuss acid-base character for the oxide and element in for the oxide of period 3. Okay, so as we all already generally have the idea, metals is always to form basic oxide,
while non-metal always form acidic oxide. Okay, these are the trends that showing to you. So what are the things that we are focused in this subtopic? First, we have to know the formula oxide for each element. Okay, so oxide, just keep in mind that always as the oxidation number O2 negative. So with the Na is always Na plus, so change it Na2O. Okay, so we have Na2O, MgO, Al2O3, silicon oxide, P4O10, SO2, Cl2O. Okay, beside the formula, then we have to know their nature about either they are acidic, basic, or amphoteric. Okay, so as we already discussed just now, metal generally going to form basic oxide. However, we have one example here, which aluminium is metal. But this metal can show both acid and base character, so that's why we call aluminium oxide is amphoteric oxide, while others non-metal are going to form acidic oxide. After knowing the acid-base character and also their formula of the oxide, then now we are going to use chemical equation to prove that why we know that metal is showing basic properties. Okay, so we have two type of chemical equation can be right. First, we try to dissolve the oxide in the water. If it can form OH negative, then it is alkali. Okay, another one is acid or base always will react with acid. Okay, so we will try to use the metal oxide to react with acid, and then supposedly will form salt and water. Okay, so either one of these chemical equation can be written so that you can prove that metal oxide is showing basic properties. So for example, if we have sodium oxide react with water, they will form NaOH. So the solution form contain OH negative, so means that the solution is alkali solution. So if it is alkali solution, so metal oxide is basic. Another example, magnesium. In this case, we say it is base. HCl is acid. So both acid and base react will form salt and water. As we discussed the basic oxide, then next is the amphoteric oxide. Like we mentioned just now, example of amphoteric oxide is aluminum oxide, which show that they can show both acid and alkali solution. So in this case, because we know that acid is HCl is acid, so means that in first equation this aluminum oxide will act as the base and produce salt and water. Okay, then next equation, when we look at here, this is NaOH. NaOH is a very common base. So then we will know in this case, aluminum oxide is act as acid and then to form salt. Last part, non-metal oxide always will show acidic properties. Okay, so same case as well, we have two type of equation, either dissolve them in the water. So if it is acidic solution, it will produce H+, like what we learned in chapter 1. Okay, and acid also will react with base to form salt and water. So let's take the example here. SO3 react with water will form H2SO4, as we all know. This is a very common acid, which is sulfuric acid. While for the SO2, we also will form acid. So NaOH is the base. So acid and base react will form salt and water. Okay, let's continue with the tutorial question number 8. Complete the following table based on the property of oxide in periodic table. As we know, sodium is metal, so will be basic. Base, magnesium metal also base, Okay, but then we know aluminium is a special case, is in between base and acid. So we call this the basic oxide is amphoteric, while for the silicon is acidic. Okay, because all these are metal, so the bonding between them with the oxygen is ionic for sodium, magnesium, and aluminium, while for the silicon, it is covalent bond. Then now we want to look at the formula of the oxide. As we know, if this one form an ion, they prefer as the Na plus, Mg2 plus, Al3 plus, and this one will become Si4 plus. Okay, so Na plus and O2 negative, oxide is O2 negative, so we cross over, the charge will get Na2O, cross over Mg2 plus with the oxygen, we will get O2 negative, we will get MgO, while for the aluminium oxide, we will get Al2O3. So for this one, we will get SiO2, which the case is quite similar with the magnesium. Okay, question number B, write the chemical equation to show the amphoteric properties for the aluminium oxide. So because aluminium oxide can show both acid and base, so means that we need two equations. Okay, the first equation is here. Because of the HCl is the acid, so we know in this case the aluminium oxide is add as the base. While another equation, we need to show that aluminium oxide is acid, while the other one, OH negative, is the base. So these are the answer. So we are completing chapter 3, just left the part of objective. Okay, we are at the end of the video. So this slide will show you the objective answer for tutorial chapter 3. So thank you for watching this video. We will continue with chapter 4 in the next video. Thank you.